Good afternoon, everybody. I just like to welcome everybody to this presentation. It's part of the ESCOM webinar series. Our presenter today is Dr. Jacqui Crozier, and she'll be talking about defects, degradation, and characterization in PV modules and cells. Just a brief outline of our speaker. Dr. McCleland is a senior researcher in the Photovoltaics research group at the Nelson Mandela University. She graduated with her PhD in 2014 and has been working in this field since her graduate years, focusing on defect characterization, electroluminescence and using techniques like that. At the moment, she is the, in addition to being the researcher in our group, she also manages the photovoltaics testing laboratory, and that laboratory focuses on module testing according to ISO 17025 standards, and essentially to look at quality testing and to verify performance. Jacqui is an active researcher, and she focuses her research at the moment on module degradation and the improvement of lab-based and on-site testing techniques. She's actively involved in supervising postgraduate students at master's and PhD level, and has also authored several scientific journal articles and international conference presentations and many local conference presentations. I think Jacqui is suitably qualified to talk to us about this on this topic. So I'm going to hand over straight to Jacqui right now. Jacqui, over to you.
Thanks very much for that introduction, Prof. I'm very happy to be able to talk to everyone about photovoltaic cell and module characterization techniques. And we are going to focus and look on different defects and degradation modes that exist for photovoltaic modules, and then also look at the characterization techniques that are commonly used. So this is the outline of what we are going to be discussing in this webinar. So when one is assessing the costs of a photovoltaic system and looking at ways to reduce costs, obviously any increase in the reliability and the service lifetime of a PV module will result in a reduction of costs. So typically looking at current degradation rates, the power rate of crystalline silicon PV modules decreases at 0.8% per year. So it is important that this degradation rate is monitored and minimized as much as possible in order to ensure that the modules reach their full lifetime. So the module design of a typical PV module is explained in the slide. So cells, individual cells are connected in series and to form series, to form cell strings, and then these strings are then connected in parallel within the module. So a cell consists of bus bars, which are an electrical contact on top of the cell material, and then the grid lines or grid fingers or contact fingers then run perpendicular to the bus bars. Then the module is made up of the front surface of the module would be a glass layer, followed by an anti-reflective coating, and then there's an encapsulant that sandwiches around the cells themselves. So this provides a buffer layer to protect the cells because they are quite brittle in themselves. Also provides an electrical insulation. It insulates the modules and the cells and encapsulates them from any environmental factors. And it's the material that's used should also have then a low absorbance in the particular PV solar spectrum. So the common encapsulant is an EVA. And then typically the rear cover would be a opaque material like a Tegla. But that previous slide, I would say, is traditionally how the PV modules are made, but there are obviously new developments happening all the time. So one of them is bifacial modules, and this is where the back surface of the module is also transparent. And then this allows additional production from the back surface of the module. Then there also are various developments happening to improve the efficiency of modules. This includes using half cells, connecting these then in parallel within the module, and then different materials. So this is quite an interesting developments that are happening in the PV industry. So we're going to probably include some more discussion on this in one of the upcoming webinars we're going to have. So as the modules are also growing, they're getting much bigger than the size that one would typically see, and these pose different challenges for the characterization techniques that we use. So this presentation will focus on some of the existing work that we've done on the more, I won't say traditional, but the more standard module configurations. So just to give an introduction in how any degradation or defects will affect the performance of the module. One can start at the very basics and look at the cells within the module. So cells are connected in series within the module, and then the voltages will add, and the currents are equal, or alternatively you can look at the currents. The current is limited by the worst cell in the series connection. So when we have two cells like this connected in series, and they both are producing the same amount of current, then the current that is generated by each of them is the same as the current that is flowing through the external circuit. So each of these grey boxes represents an electrical element of a solar cell, which is the photogenerated current, and then a diode representing the solar cell. So these cells are short-circuited, so the voltage across them is 0, and the short-circuit current is flowing through them. Here we're in a situation where one of the cells is shaded by 50%, for example. So this shading could be due to a number of factors. It could be literally shade on a cell, shade from another building or a tree, or some form of vegetation that's blocking the light to that cell. Or it could be shaded by soiling, which is dust accumulating on the modules. Or it could be have decreased performance due to a defect or a crack within that module. So for whatever reason, this, a defect within that cell. So for whatever reason, this cell 2 is producing 50% of the current compared to the other cell in series that it's in series connection with. So this results in the weak cell, which is cell 2, becoming reverse biased, and in that way it becomes a power dissipator and heats up and forms a hot spot, which can result in further damage to that cell or the module, or a safety risk to the module is present if there's a significant hotspot. So to some degree, this effect is minimized with the use of bypass diodes, which are standard in all crystalline silicon PV modules. They are connected in a module in parallel over a string of cells. In these illustrations, it illustrates the effect of a bypass diode connected in parallel over a cell. So in the instance where one of the cells is shaded by 50%, what would happen is the current is now mismatched. So the cell 2 that would normally have become reverse biased and heat up, this cell now, the bypass diode, is activated across it. So this conducts the extra current, let's say, and in that way prevents that hotspot from occurring. It does affect the performance of the module in total, and we will see in later slides how the activation of bypass diodes affects the module and stream performance, but it prevents any catastrophic damage. So the difference between a module failure and a module defect, just to be clear of what's we're describing, is a module failure is described as any effect that significantly degrades the module power and cannot be reversed in any way by normal operation, let's say, and also it might create a safety issue. So things that like soiling or shading are not a module failure per se. Something like a module defect is something present in a PV module that you're not expected to see. This often when we do an EL imaging of modules, we pick up variations in the material, which is not necessarily having a significant effect on the module performance. So to move into some of the degradation that one can see in PV modules, the first one we'll look at is encapsulation degradation. So this is where the EVA, which is the encapsulant that surrounds the cells in the module, starts to degrade, and it results in the buildup of acetic acid, which results in increased series resistance, and also contributes to the effect of formation of PID, which is potential induced degradation. And this is an effect where this EVA goes into a yellow-brown color that one sees often in much older modules or modules that have been outdoors for a few years already. And this is where this brown color occurs over the cells in the module. Similarly with the layers or the encapsulation layers within the module, module delamination can occur. So this allows then water or moisture or air to get in between the layers of the module. And this effect can get better or worse depending on the well, not better or worse, it can vary depending on the thermal and humidity and environmental effects. So any module delamination in the layers is classed as a module failure. So just briefly touching on potential induced degradation, we are going to have a webinar that looks at it in more detail in the next few weeks. But PID occurs when there's a high system voltage that causes leakage currents between the glass surface and encapsulants. And this results in a loss of power. And it's very much dependent on the system voltage of the system, and the environmental conditions of the installation. But it's visible in quite clearly in EL images, where you start to see a checkerboard or a variation in EL intensity. So this first image is an EL image of a module without PID, and the second second image is the same module after PID has been induced in it, and you can see the loss of intensity in the image that's related to a loss in module performance. So all these degradation effects will have some effect on the IV curve. So the IV curve is measured of a module or a string, and from it the module performance parameters can be extracted. So the short circuit current, the open circuit voltage, and the Pmax, the maximum power, can be extracted from the IV curve. But it is also important to look at the actual shape of the IV curve, and because that provides additional information about what is actually happening in the module or the string. So if you have an increase in series resistance in the module, for example, if there's a corrosion of contacts or an effect like that, you will see the IV curve move away from the knee, and you have a lower Pmax point because of this increasing series resistance. If you have a decrease in your shunt resistance, which also occurs through the occurrence of PID or due to metal migration through the PN junction, then the IV curve will drop down in this region due to the decreasing shunt resistance. So an effect like shading can also be picked up in the IV curve of a module or string. So in this slide, we look at the IV curves of a string, which is shaded by a installation in front of the system. So it's a 3 kilowatt system consisting of 2 strings. So there's a string at the top and the string at the bottom. The bottom string has shading on 2 of its modules, 2 of the modules within the string, which results in 3 cell strings being affected. But you can pick that up when you look at the IV curve of the shaded bottom string, which is the blue IV curve here, where you can see a series of bumps which are indicating that a bypass diode has been activated. So a bypass diode over a cell string would be activated if there is shading or some mismatch present. So when you look at the performance parameters in the table, you can see that amount of shading, which on these 2 modules, can result in 200 watts being lost from the STC Pmax value. So if one were to just look at the performance parameters by themselves, one often doesn't see as clearly the activation, that there might be a cell mismatch problem, whereas when you look at the IV curve, these sort of jumps in the IV curve indicate that there must be bypass diode being activated. So front surface soiling is anything like dust or dirt or bird droppings occurring on the front surface of the module. So with something like dust, it's a very it can be a very site-specific factor depending on the conditions, the environment, the rainfall in the area, and this results in a soiling rate that they must be accounted for in any long-term assessment of the module. The site performance. So it's cleaning of modules is an important aspect to this. Dust is normally a very uniform covering the module unless it accumulates at the bottom of the module, which is often happens. But if you have areas of the module which are more soiled than others, then you have that potential of that cell being significantly performing significantly worse than the other cells in the module and becoming a hotspot and reverse bias, as we had illustrated in the introductory slides. So cleaning of modules and removing of any front surface soiling is something that should be considered important, and obviously depending on the site and the location of the PV installation. So modules are made of have a glass front surface, so obviously there's always a risk that glass breakage can occur in the transport or installation or handling of the module at any point. The glass should also the installation of the module in the racks can also result in stress to the module that can result in glass breakages. And as these modules become bigger and more difficult to handle, there's always a possibility that they can break during installation. But these are very obvious breakages, and obviously if you have a module that looks like either any of these pictures on the slide, you would know that you should not, it counts as a module failure and is not suitable to be installed. So common defects in a PV module can be detected using electroluminescence. So while we said that the glass can break, there's often instances where the glass does not break itself, but the cells can break. So this is when a microcrack can occur. So a microcrack is a crack within the cell itself, and you can see it visible in an EL image. And it's possible, depending on the location of the microcrack, that it will result in an inactive area, which is an area of the cell that is completely removed from electrical contact. And in that way, it cannot generate current, and it limits the performance of the module. Similarly, you can have a disconnection in the contact fingers that run across the cell, and these are also then visible in the EL images as an area with a decreased electrical contact. So cracked cells are fairly common in PV modules. They can occur during transportation, installation, and really any point during the module's life. But the effects that they have on the performance of the module are related a lot to the orientation of the crack and the area that is affected. So once you have an area of disconnection, then you obviously will have an associated power loss. So to combat this, newer modules have moving away from the style of having newer modules won't have 2 buzz bars that are illustrated in these images. They'll have 3 or 5 or some even up to 9 buzz bars. Because once you look, I mean, if you look at these cells in these images here, if you can imagine there being more buzz bars, then the effects of these cracks becomes less and less significant, because you would still have the other buzz bars to provide electrical contact. So snail trails are an effect that one can visibly see in a PV module. So it's visible as a sort of silver line across a PV module. So this example here is maybe has a lot going on, but you can see this half circle shape is the snail trail. These white marks here is a degradation in the anti-reflective coating. But what happens is the snail trail normally always will correspond with a microcrack that can be detected in an EL image. So the discoloration then will give you some indication that there are microcracks present. So normally what would happen is if the module were damaged, snail trails do not immediately appear, but with time the paste, the silver paste on the front surface of the module metallization then reacts and results with that pattern. So, and this is also, not all modules will have this effect. It does depend on the makeup of the module components. So in the previous slides, we've introduced a lot of defects using EL imaging, electroluminescence imaging, as a way to describe them or identify them. And this is because EL really has become a very important imaging technique for assessing PV modules, assessing quality, giving an indication of any defects present, and ultimately monitoring the degradation of a PV module. So electroluminescence is detected when you forward bias a PV module. It then will emit light in a region that can be detected by your EL camera. And any areas of the module that are not electrically connected will appear dark, and the rest of the module will show up as light. So as I said, it has become a very important technique in assessing the quality of PV modules. So you can, in common lab tests using electroluminescence, it can be done at 2 levels. One, the first level being 110% of the IC of the module, so it means you're forward biasing the module at 110% of its IC. Then this gives a very clear image that you can use to identify any cracks or defects within the module. So these first 2 images show where microcracks and module defects are present. Then in the third image, at 110% IC, there are no obvious defects. But when you do EL imaging at 10% IC, which is what's illustrated in the fourth image, you can see this checkerboard pattern of cell intensity varying a lot but from one cell to another. And this is often indicating some form of PID present in the module. So the third module and the fourth module are the same module, just done at 110% and at 10%. And you can see at the 10% IC, you can pick up this PID clearly, whereas it's not clear in the 110% EL image. So the quality of your EL image is defined by a few parameters. So the sharpness of an image is important. So this is defined in the IEC standard for, which is a technical specification for electroluminescence imaging. And it defines the sharpness by the smallest resolvable object that you can resolve in the image. So class A is appropriate for laboratory measurements. The EL images are presented so far in this presentation have all been laboratory quality measurements. Obviously, when you get to larger scale industrial on-site measurements, then your sharpness does not need to be as good. An on-site EL measurement, you would really be looking for very significant areas of disconnection. You would not be picking up small microcracks from on-site measurements. So the resolution of the image is determined by the camera used and the setup used. So the more cameras you use so that you can take a single module EL image, make it up of several images and stitch them together, then you'll end up with a better resolution image. And then also any noise in the image, you want the highest possible signal to noise ratio possible. So you can ideally EL imaging in as dark a condition as possible. A lot of some cameras will have filters that allow you to do it in low light conditions, and also the background image can be subtracted from the EL image to remove any effects of stray light, dark current through that result in noise in the image. So visual inspection is an equally important characterization technique. It's often seems a bit obvious because if a module is broken, it looks broken, but there is a value in identifying very quickly any failures or issues in the module using visual inspection. So detailed in this table are the features that we would look for in a visual inspection test. So any delamination, any loss of mechanical stability of the module, the frame damage, all would be noted during the visual inspection test. So maximum power measurements are done indoors using a solar simulator. The rating of the solar simulator is defined by how it meets these three aspects. So this standard, I think, has actually been updated since has been updated more recently, but you would be judging a solar simulator. Obviously it has an artificial light source, and you would assess it based on how well does this artificial light source meet the reference spectrum. So you would want it to have a similar solar spectrum to the outdoor solar spectrum. You would also want to have spatial uniformity, so meaning over the test area, the area in which the module is placed and tested, you don't want to have one corner be significantly brighter than another corner, because then you're inducing a mismatch effect within that module. And finally, you would want there to be a temporal stability, meaning that over the period of measurement, the light source is stable. So this IV curve at the top shows the effects of different shading patterns on a string of modules. So it's quite clearly shows that you know, when you're looking at the IV curve, you can see how you can assess from an IV curve what sort of shading effects are present within the string that you're assessing. So the final characterization technique that I'll discuss is thermographic imaging. So this is one of the most common fault-finding techniques for a PV installation, would be to assess with a thermal camera PV modules under operation. So they can either mount a thermal camera on a drone, or they can walk through the PV installation with a thermal camera and look for any hotspots. So this image here shows how even a small corner of shading can result in a fairly significant hotspot, and might not even be picked up as being a significant issue other than from the thermal image. So we will have another webinar which will look at all the issues and intricate interpretations that occur from thermographic imaging of a operational PV installation in the next few weeks. Thermographic imaging can also be used in a lab-based setting. This image here is a module that's been forward biased in order to detect areas of excessive heating. Again, any hotspots on the busbar or the cell can be detected. Ultimately, in a lab-based setting, electroluminescence does provide a lot more information than thermography, because when you do an EL image, you'll see exactly what is causing, you get a clearer picture of the cracks or the problems. Thermography in a lab-based setting does have some limitations. So hotspots again occur when there's a mismatched, shaded or damaged cell, anything that can limit the current produced by the cells in a series connected string. And yeah, they can result, a mismatched cell can result in quite a significant hotspot, which then can cause a burn or a fire hazard in some way. So it is very important that these mismatched cell issues are detected and dealt with when they are found. So the Photovoltaics testing lab is part of PV Insight, which is which provides SONOS accredited PV module testing services. Some of the tests I've described in some detail in this presentation. We offer vision inspection and maximum power measurements, as well as the electroluminescence imaging, which we discussed during this presentation. In addition to the lab-based tests, there also are on-site tests that can be performed on large PV installations. This includes outdoor EL imaging of modules and strings. So in the corner of this slide, you can see a EL image of a module string and indicating where there are where there are problems in the modules. But as you can see, there's a far lower resolution than you would get in a lab-based EL image. And this outdoor EL has to be done at night. So that's the other challenge. That on-site measurements of strings, IV measurements of strings, we discussed as well as thermographic inspection. And so these testing facilities are accredited through PV Insight, and the PV research group does contribute by the research into the outputs and advancement of these characterization techniques. So my final slide was just an acknowledgement to the PV research group, ESCOM and PV Insight for the results that were presented today.
Thank you very much, Jacqui. Very interesting presentation. You can see all the work over the years that's been covered, and I think you really encapsulated the key aspects of the characterization tools and techniques that are needed for properly assessing defects and degradation in PV modules. I know you could have carried on for very much longer, but thank you very much for that presentation. I'm going to now open up and ask if there are any questions. Please publish these in the Q&A. Just type them in there, and we'll address them as they come up. Jacqui, while we're waiting for the participants to load or to ask questions, perhaps you can just go back to one of those slides where you showed an IV curve with the shading. I think that one particularly with a small amount of shading on the lower string of the array, and we got a significant amount of degradation or power loss, yet the shading was actually, that one, the shading was actually very small. If we look percentage wise, it's a very small amount of shading. Perhaps you can just elaborate on the fact that the performance loss does not have a linear relationship with the actual shading.
Thanks, Prof. I think what had happened here, is when you look at the strings that are affected, so the shading here on this module is probably affecting one cell string there, and in the module that's closest to us, then there's now two cell strings affected, because the cell string would be this. So I think what's probably happening is because there's so much multiple strings are being affected, you're having a more significant effect. Whereas if all of the shading, so the same area of shading, was focused on just one string, then the bypass diode would be activated, and that string would be knocked out, but perhaps the overall effect would be less. So this affects then and this amount of shading then is affecting your Pmax at your where you measure Pmax at the knee. But because the bypass diodes are operational, you still have the same short circuit current and open circuit voltage. So I think it is something that one can consider. The shading that you would expect should be considered when you are looking at how to orientate your modules if shading is unavoidable.
Thank you, Jacqui. We have a question come up, and I'll just read it to you. The equipment you are using for particularly outdoor testing of string IV, are they ISO accredited? Do you want to comment on that?
Yes, so we are in the process of getting our string IV, our on-site IV measurements of strings and modules accredited through Sonos. So it should hopefully be included at some point. The equipment itself is standard IV tracing equipment. So in terms of your Sonos accreditation or your ISO 17025 accreditation, you need to ensure that it's fit for the measurements scope that you're looking for and provide some measurement traceability. But we are looking at how to include that as an additional accredited test. It is currently a testing service we provide, but it is not covered by our scope of accreditation.
Thank you, Jacqui. We have one more question, and that's, Jacqui, I'm sure you can see it, but I'll read it for the participants. To what extent should a module be able to handle mismatch shading over a long period of time?
I suppose that is referring to if you know how, I suppose that means if there's some sort of like shading that's resulting in a hot spot like we saw in that thermal image, how long should that module be able to deal with that level of mismatch before it's a complete failure? I think that's probably very much dependent on the type of module and the situation present, and I think that's why the steps that they are the next generation or next improvements in PV modules are really looking towards the fact that they can deal with a fair degree of mismatch without a catastrophic failure or a complete failure of the module. But yeah, I can't comment to a specific time or a scale, time period.
Thank you, Jacqui. I think when the thermal imaging presentation is given by Montes from Woodward, he'll touch on the extent of the damage or the power loss, and that would also give one indication of what would happen, over the long term. And as you rightly said, different technologies are more susceptible to shading or the effect of shading and cannot handle it at all. So yeah, it is very much a question of the extent of the shading. Is it a transient effect? Is it permanent? All these have play a role and will obviously make have an impact on the the lifetime of the module. I believe there is another question. Jacqui, can a broken module or cracked module cause fire if not attended to?
Yeah, I would imagine that would link back to then the degree to which the degree of the damage. So if there's a failure in the electrical connections, but you know, something like the thermal image, obviously there's a significant hotspot present that's that could result in a fire in the right conditions. So I think that's why this the erring on the side of safety would be to, at a certain hotspot level, replace and remove a module.
Okay, thank you, Jacqui. So in essence, it's yes.
Yes.
Yeah. So I think I don't see any more questions. So from my side, I'd just like us to wrap up, and Jacqui has acknowledged a few institutions. I'd like to just acknowledge the acknowledgements again. Now, obviously, this is an Eskom webinar. It's part of our project with them. The Photovoltaics Research Group supplying all the results and data that Jacqui used. Our government sponsoring partnership with the Department of Science and Innovation, obviously PV Insight. And then, of course, last but not least, Chanel Roby from NMU IT Services, who is always willing and very able to assist us in putting the program together. And then, just in terms of the just please watch the space. We will be advertising the next round of, well, the next webinar, and I think that's in approximately 2 weeks' time, and that's going to be on the more detailed characterization of modules using electroluminescence and IV characterization, and that will be done by Roslik Speak. And I've just been given the date, it's the 19th of March. And then again, another one on the 26th, and that will be the thermal imaging webinar. So with that, I'd like to wrap up, and thank you very much to everybody for attending. Goodbye.